Welcome everyone to FDL-X Live, our presentation today of some amazing scientific and machine learning results. As a quick introduction of myself, I'm Ann Spalding. I will be hosting us through this session along with James Parr, who will be both helping to host a little bit, but also being the time tyrant. And we'll hear a little bit more about that in a moment. But let's go ahead and jump in to what we're at today. So this is a presentation of a bold experiment. And the experiment was, can we mature machine learning and science aspects of three challenges while building an integrated AI pipeline to unlock powerful new capabilities for NASA Heliophysics and space exploration? That's a very bold experiment. And to make it a little bit more bold, we were doing this over the course of an 8-week sprint this summer with a research team. During the next hour, we're going to present to you the results of that experiment, in addition to insights from our esteemed panel that will be talking to you about both the advances that were made on these challenges in machine learning and heliophysics. In order to do that effectively, we'll be giving you a heliophysics primer, and then we'll have a presentation followed by panel insights for each of those three challenges. For the audience, we are not going to do any open Q&A, but we encourage you to, if you have any thoughts or questions, log those down. We'll give you some ways to connect with us later. And as a quick reminder, again, to my presenters and panelists, we're working on a very tight timeline. So please keep your responses and your presentations pithy and short so that we can get good insights from everyone. And James will be more than willing to help you along with that with his exciting time tyrant sounds coming out. I talked a little bit about we're working off of existing challenges, but what's most important and what's most important for today is there's no way we would be here without the help of our partners. And so I want to take a moment to just thank each of them, and then you'll get to hear more from them in our panel. So first partner is Massimo Mascaro from Google Cloud. Google Cloud gives us the digital cloud platform where we are able to do all of the machine learning compute that enables these challenges to go forward. In addition, we have Alison Londas from NVIDIA also providing their DGX support. The compute power from these two partners is what makes FDL happen, what makes FDL possible. And so I want to have a huge shout out to them. Not only were they giving the compute power, but also a lot of support to our researchers and our faculty as they onboarded onto these machines, producing tutorials, jumping on in the middle of the night to give support, really leveling up so that we were able to get to the results that you'll see today. And then, of course, NASA. So NASA is our partner, both in devising what this challenge would be, all the way back at the design phase and funding it, and then throughout the summer and ongoing, really helping us align what we're doing with the research to the science that's there. So I want to welcome Lika Hunju and Mike Little from NASA. And again, you'll hear from them throughout the session today, but we would not be able to produce this without their support. And we're so excited to have them with us today, and you'll get to hear what they have to bring to the program. And then finally, as I mentioned, this project was over the course of 8 weeks and then is ongoing research. And that research comes from our team of faculty and researchers. So we have 3 teams, and the 3 teams are made up of 6 or 7 researchers and faculty. Some of those you will hear from today, but I want to send out a thank you to this amazing team and all the hard work that they put in, the results of which you will get to envision soon. With that, I want to hand us over to Andres to give us a brief Helio primer that's going to set us up for understanding the importance and the impact of these challenges. So Andres is sharing a screen.
Okay, so I just want to give the context of what our teams are working on because they are made in the context of the interaction of the sun and the earth. So the main things that I want you to remember, take from this primer is that solar magnetism is the main driver of solar variability. There are 3 main ways in which the sun interacts with the earth: through light, magnetic fields, and particles. Light changes the density of our upper atmosphere, which affects our assets in our low orbit satellites. Magnetic fields induce currents in our atmosphere and the ground, which affects long-distance transmission lines, electric transmission lines. And particles affect assets in space in degradation, in the form of degradation of hardware, and also irradiation of astronauts. So to understand the interaction of the sun and the Earth, it's very important to understand that the sun is a magnetic star. Here you see sunspots, which is the optical representation, like manifestation of very complex magnetic fields in the surface of the sun that you have here in color. These magnetic fields give structure to the solar atmosphere, which you can see in ultraviolet. So they act as an skeleton that gives structure to the corona, the solar atmosphere, but also they provide the excess energy that drives space weather. Okay, so when we talk about, the interaction between the sun and the Earth, I think that's the first thing that I wanted to mention. Ultraviolet, which is this image that we have here, and is one of the things that one of our teams worked on, is one of the main things that determines how the upper atmosphere of the Earth breathes. So from time to time, you have these very, very strong energetic events that significantly increase the amount of radiation that we get from the sun. And so this takes our upper atmosphere that absorbs all this energy, and it changes its height and density. And that means that satellites that would have been almost in vacuum now are subject to a prolonged drag that reduces their lifetime. They also accelerate particles that are highly energetic, that degrade in hardware in space, but also affect astronauts in space. Now, these events can trigger the release of very, very large amounts of magnetic fields and plasma into space in the form of these coronal mass ejections, which you're seeing here, one. And these are events that span the entire solar system. So these are huge events. And so you can see here, so you're going to see one of these events happening, and it's going to be huge. Okay, so the sun is this big, the Earth is but a mote here. So here you have a simulation of the magnetic field of the Earth and how that magnetic field of the Earth responds to an event like this one. So you can see that we have our magnetic field, and then suddenly when the event, there is a huge disruption and modification of this, of the magnetic field of the Earth. And this is important because changing magnetic fields induce currents. And so we have the Earth and our shield, and changes in this induce currents in our atmosphere, and it also induces currents in the ground. And this is another thing of one of our teams is looking into. Now, the last thing is this atmosphere of the sun is extended and actually extends all through the solar system in the form of what we call the solar wind. Now, the solar wind has different speeds and has a lot of structure imparted by the corona itself, the atmosphere, the lower atmosphere of the sun. And when you look at an image of the sun in ultraviolet in another wavelength, you can see that there are these dark regions called coronal holes. These are the sources of the fastest solar wind, which can be 2 or 3 times faster than the solar wind that comes from these bright regions. Now, when sometimes, and this happened in September of 2017, one of these extends into the equator. And it basically means that, these combinations of fast and slow solar wind gives a lot of structure to the solar wind in the solar system. Let me see if and creates this kind of beautiful spiral structures, but where the fast solar wind is catching up with the slow solar wind and enhancing density. And when they hit the Earth, it creates a lot of disruption. And so when we go back to this video, and we know that the Earth's path goes through the equator of the sun, and we have one of these events, one of these crossings, then this sets the stage for the joint study event that you're going to see in our demos, where there is this coronal equatorial hole that crosses the Earth's orbit. It creates this high-speed particle stream interaction event, and it created one of the strongest, a relevant geomagnetic storm during that time.
Wonderful.
I'll give it back to you.
Thank you so much, Andres. James, I saw you unmute.
Well, I was just going to warn everybody. I have my girl's Halloween soundbox for me to be the time tyrant, and so I was gonna do the bell toll. But you were perfect timing, Andre, so I didn't have to do it. But next time I'll be ready.
Nice. So, with that brief introduction to heliophysics, what we want to talk about for the rest of the session is what are some of the ways that we can help predict and look at what's happening in those events from the sun and understand them better on the Earth. And so, as we mentioned in the beginning of this, we had 3 challenges that we were trying to mature and integrate. So the original 3 challenges were ones that were produced in the last several years through our FDL research program. And what we worked on this summer was taking each of those and not only maturing them, but also integrating them into a single pipeline. And we did that through a really innovative approach into our team dynamics. And so the integration was not only on the projects themselves, but also on the team and how they work together. And the 3 challenges that we're going to hear about today and the questions that they're going to answer are from our ARD EUV team. Can we create an EUV data product that's usable by the community? From our thermospheric drag team, can we better understand the importance of EUV on thermospheric drag? And finally, from our geoeffectiveness team, can we understand how geoeffectiveness is on a regional level on the Earth? And so without further ado, I'd love to hand this off to our first team, which is the ARD EUV team. And Richard Galvez, if you can share your screen.
Sure. Thanks. Just a second. I'll set up a timer on my end as well. I'm gonna be sure.
This is the sound effect you can have.
Okay, I'm ready for it.
All right.
Okay. All right. I'll share my end now. Okay. All right. Let me present. Oops. Actually, I'm gonna go back. Okay. So can you all see my screen all right?
Yes.
Okay, great. Okay, thanks, Anne, for the intro. So as was mentioned, one of the sort of core challenges to what we envisioned with FDL-X was to not only create this data that would other teams could utilize and be kind of ready for analysis and machine learning applications, but also the computational sort of platform around that. So that's where we stepped in. So we had a great group of researchers. We had a lot of fun this summer. Will Fawcett, Manuel Indico, and Daniel Gass. And then the faculty, led by myself, Andres, and Paul, probably familiar names by now. So just to recap, then the Solar Dynamics Observatory was the main, the SDO mission was the main data source that we're utilizing. And this is made up of 3 main instruments. That is AIA, a 10-channel imager at different wavelengths, the Eve irradiance measurement tool as well, and HMI, which is a magnetic imager. Now, the real sort of upshot for us is to understand, at least in the context of our challenge, is that there's massive data. So it's like 20 petabytes of data that is large for anyone, really, no matter the scale that you're at. I know Google's in the audience here, but even for you, I think 20 petabytes is a lot to deal with. So we have this situation where scientists need access to curated data, but not only that, also the compute resources that go along with performing large-scale data analysis. So there's a clear need for an automated pipeline to prepare and to serve this data. So enter the SDO scientific computing platform. So we kind of realized that we had to create this along the way. That is really a platform that allows for the analysis of this data. It's serverless. It's built on top of GCP. Thank you very much, GCP, for the resources. And it scales up to meet the needs of the compute, which was the real fun part. And though I could say maybe it's not as complicated as it looks, well, maybe it is a bit complicated, to be honest. But the nice thing is that it works as expected now. So we're quite happy with that. But one of the main first things that has to happen with this infrastructure is that we need to take in data from various sources, in particular the JSOC, and process these in order to have them ready for analysis for the team. So that's AIA data and HMI as well at various resolution, different cadences, as could be seen here. Now, the real kind of interesting aspect about how this all works together is that there's a scalable compute orchestrator at the heart of this. So from here, we have jobs that scientists on the right or users can query this system to organize what kind of data processing they need, to come in from the original source. But not only that, the kind of compute that they would like for it to affect. So we have API compute endpoints, so you can create the means or standard deviations of various signals, or ML API endpoints, so you could maybe create some inference from some model that you produce. Then after that, the data products on the bottom here are stored in buckets and databases that are accessible to the community at large. So just to give you an idea of how this pipeline looks in action, I have this figure here, which I'm quite excited about and happy about when everything just kind of works the way you want it to. We have 6,000 concurrent machines running at the same time that was ingesting data from JSOC and processing it at the same time. So we're quite happy that worked great, and probably turned on an entire a few racks at the GCP US Central 1 region data center. So as a case study, present this virtual instrument that we created, so one issue was with the Eve instrument is that the MEGS-A ion channels broke a few years into operation. But there was some sort of idea that from a physics perspective, we could recreate that signal because the AIA imager also have overlapping wavelength. So we created a CNN model along with a linear model that reproduced that signal. And we did so much further than any other team had done in the past. That's because we also developed that computational back end to really make it happen. Now we also have this live data, which we would very much like for you to go to. It's sdomldemo.org. We have access to this inference data. And not only that, coming very soon, we're going to have the latest irradiance measurement, the past 5 minutes. So you have up-to-date information. So visit us at sdomldemo.org. So with that, we created the computational platform that we believe SDO always needed, never had. We have SDO-ML v2, the data product that was needed for this. Also, Virtual Eve as an observation or an experiment that showed the utilization of this and as an impact. So we built this system that we believe SDO always needed. And so, now we have this sort of toolbox that we can show the rest of the community how you can build large-scale scientific computational cloud-based data analysis tools. So some open science questions we have at the moment. How does HMI, does it ever become useful for generating solar radiance? We figured out that at 512 by 512 it did not, but maybe at higher resolutions it does. Also, what other parameters or input can be provided to improve the model predictive performance? So some questions that you can see here. Also, could embeddings straight from 4K images provide more manageable and practical input for training? What about embeddings? Could we create an SDO foundation model? But now the nice thing is that we are in a position where we can answer a lot of these interesting questions because we built the sort of computer infrastructure around the data to be able to make to answer these questions. So next steps, we continue to use the system that we built. We would like others to use it as well. And as a kind of ambitious thing, hopefully ready by the showcase, is an SDO foundation model. So with that, I'll conclude. Thank you. Anne, I think you're muted. Yeah, I was like, wait, did everybody just jump off? Was I talking about myself here?
There we go. Can you all hear me now?
Yes.
Okay.
I was going to say, Richard,
thank you.
Your data throughput rate is extremely fast. Just yourself that was awesome. I didn't even have to use my bell.
Thank you.
Nice. Wonderful. So now we'd love to open it up for 10 minutes discussion from our panel. And panelists, if you would briefly introduce yourself as you come on, that would be great. I'm going to allow you to kind of popcorn through some questions or just general discussion that you have on it. But just so everyone here knows, our panel is, again, Masi from Google Cloud, Allison from NVIDIA, Lika Hunju, and Mike from NASA, and then Andres and Tom, who are both our faculty research, but are also heliophysics and ML experts coming through. And I will stop share so that we can see our panel. And Leora, if you can help me be penning those folks so that we have them up front. And I want to just launch off with our first question to the panel, which is, have you seen this type of live inference project before, and what is the impact of it?
I'll take that then. I mean, I was part of this effort, but I think this is one of the things where it becomes challenging to really, take advantage of this data. It's really hard to access, it's hard to process, it's hard to store. And, when it comes to more like an operational setting, we need that to happen right now so we can make informed decisions right now. And so I think that's what I would like to highlight, this. We're building on top of what the FDL has done before, but we have taken it into a level of readiness that is unprecedented.
I think, yeah, that's why we call ourselves NASA. NASA's goal, especially in the Science Mission Directorate, is to fly missions in space to take advantage of the vantage point of space for both Earth and space science. And we collect enormous amount of data, and that is our most prized possession, because it is with that observation, that data, that we are able to answer our important science questions. And Solar Dynamics Observatory happens to be the cornerstone mission for the Living with a Star program. And, it's kind of an ideal platform with its multiple instruments and a large sort of temporal baseline, right? It creates it to be absolutely suitable for today's multimodal foundation model. As Richard was mentioning, it's a new category of machine learning models trained with large-scale data so that it is generalizable for a large range of use cases. And so while NASA does not do the prediction of space weather, we do the understanding of space weather, without which we can't predict. So all of these have come together, and it's not just ARD being ready right now, but ARD also being applied to all of the successive models that we are going to look at. So this is what you have done, is really going to enable the scientific community to take advantage of this very rich data.
Wonderful. Thank you, Lika. Massey, do you want to jump in?
Yeah, I was about to double down on what Lika said. I think, first of all, congratulations. This is awesome. I think actually the thing actually I would point out is that lots of data is usually very, very good to have and very, very useful. But actually, when you can actually kind of process this data with low latency, the value of the data becomes 10x, right? The clear kind of parallel here is, of course, with the kind of, Earth weather, where you can collect, and we do collect, kind of a lot of data across the world. And actually, that data is very useful to understand how the climate works, how the atmosphere works. It's great for science, right? But what is actually even better is if you can actually now predict actually whether there is a hurricane coming and where it's going and where it's going to hit, or actually even just kind of for kind of more convenience, whether it's going to rain tomorrow or not. And so I think actually kind of part of this work actually enables that. And I think it's awesome. And I would just point out, this is incredibly difficult because, first of all, petabytes of data is not a joke, even for Google. But petabytes of data with low latency is an absolutely astonishing challenge. And even us at Google, actually, every time we try to do that, it is actually kind of a big engineering effort. Kind of seeing kind of some of this project being done in such a short time, it's just short of amazing, and kind of kudos to the researchers.
We built on a lot of your infrastructure, so thank you. And also we utilize a lot from NVIDIA as well. So I did want to also thank our other partner and NASA for the data, of course.
Nice.
Our pleasure, definitely. And it is wonderful. Sorry, I've got no camera today, by the way, everyone. Seconding everything that's actually been said, but our recently announced partnership with Google is that the DGX, so this is multi-GPU, multi-node compute, is now going to be featuring in Google Cloud, which is really fantastic. So you talked about obviously the scientific value, but the commercial value is huge, and you have to take into account, if this SDO data is now going to be available, there is a massive market out there just for things like reinsurance and the insurance companies and how this is going to affect everything about day-to-day life, with the effects that come in from these CMEs. So having this analysis ready data, this ARD with this SDO data, we haven't really even begun to think about the deployment factor, but the compute is going to be there. What you've been working with, Richard, and the team, is now going to be available in the cloud service providers, so folks can take what you've done and hopefully there's, hate to sound like an incubator, but there's value there for all of you.
Allison, that announcement of partnership makes me so happy. As our researchers were switching between working with Google Cloud and working with the DGX and NVIDIA, having those come together is amazing. And I love being an incubator. I think it is 100% what this was about.
It's actually been a big learning curve, this program, actually, this FDL program, for the fact that we're no longer dealing with single instance. Our GPUs have been in Google for years and years and years, but in single instances. But now you can actually take the entire server with all of the interconnector and all of the speed and capability and use that in Google.
Yeah, and I would double down on that, because I think the partnership we had actually with NVIDIA goes back a long time. And I think actually I don't know if we are the biggest, but we're one of the biggest customers of NVIDIA worldwide by the amount of GPUs we consume. But I think actually kind of what Allison is pointing out is that models are growing in size and capabilities. And now we need to be able to scale out, especially to do what this kind of team is kind of showing up. That is kind of to do this kind of super fast processing to kind of extract most of the information from the data in real time. And actually, that's actually where we need actually kind of things like DGX that kind of can scale out much, much larger kind of capacity. So +1 on that.
Wonderful. Well, to make sure we don't get that timer noise that James has sitting out there, I'm going to stop the panel right now and move into our next two challenges that took advantage of this data that the ARD team had and brought them forward. So next up, we have Vishal. And Vishal, if you can share your screen. And I'm going to unmute folks.
While he's getting ready, I also just want to say thank you to the researchers too. They put a lot of effort. I'm very happy with that. Thank you.
Thanks, Richard. Can you hear me? Yeah. Thank you. Thanks for confirming. Yes. Okay. I'm putting my timer also. So thank you everybody for coming here. This is the geoeffectiveness, multi-scale geoeffectiveness team. We are a team of 3 wonderful researchers, Mike, Sahiti, and Raman, and led by the faculty, Bashi, who's also on the call, Angelos, and myself. And we also had 2 very wonderful external advisors, Evangelos and Thanos, helping us out with this whole idea. We have seen, So we have seen, or Andres actually gave a very nice introduction to the whole Sun-Earth system. And what we see on the ground is basically a percolation of forcing from the sun, along with internal processes that occur on the ground. And what we see, or what we infer on the ground, is in the form of geomatically induced currents or perturbations in the Earth's magnetic field. And that's kind of going to affect, as Andres was talking about, it's going to affect your satellite systems, it's going to affect communication systems and, oil pipelines, so on and so forth. So what do stakeholders need when they ask for a good forecasting algorithm? There are 3 important points or 3 important features which stakeholders request. First is these algorithms need to be fast. They don't want to wait for the computation to occur over a timescale of weeks and then, the CME or whatever event has passed by. They want quick forecasts. They want localized forecasts. So you really see that, and for example, as given here on the screen, you have very localized enhancements in these currents, which occur over a length scale of hundreds of kilometers, and that's something you really want to detect, but not just at one location, but across the whole globe. And third, you want to get an appropriate lead time, so the companies or all these stakeholders can actually take an appropriate action and mitigate any possible effect that's going to come to them. So you can see that the Sun-Earth system is a system with multiple length and time scales. So what we have come up with is what is called the adaptive forecast refinement. So we have 2 sets of models. We have what is called sheath. Sheath is a model that ingests the solar remote sensing data, and it gives you the solar wind and IMF measurements at L1 with a very high lead time. And this time scale is across the lifetime scale of days. The lengths are around millions of kilometers. And given the sheath forecast or even the local in situ measurements of solar wind plasma, we also have what is called the Dagger model. The Dagger model was a byproduct of the FDL 2020, where we had basically a global geomagnetic perturbation forecasting scheme using deep learning. And the time scale from L1 to the Earth is about 30 minutes or so. It's very short. And the length scales around hundreds of kilometers, or thousands of kilometers at max. What also is important is the internal state of the magnetosphere. So there is a memory that is present in the magnetosphere that lasts for maybe a couple of hours and at max. And that is something that's also important for us to get an accurate characterization of what the impact of solar wind forcing is. So given the solar input, we can couple that given the solar input and getting sheath out, we can couple that to the Dagger model, which can give us low fidelity forecasts, but at very high lead times. If we have the in situ measurements at L1, we can use that to get forecasts with the internal state of the magnetospheric context also being taken into picture, and use what is called Dagger++, which is the high fidelity version which has been developed in this FDL. So what is sheath? That's basically the SDO-ML dataset which Richard was talking about, and the ARD team put together very, very nicely. And given a time series of these images, we are able to generate solar wind forecasts as shown here in the figure below. So changing images in time gives rise to these changing measurements, these changing forecasts. And once we have these forecasts, we are able to feed them into the Dagger code and present and predict and forecast what the geometric perturbations are like. So that's northward and eastward component of geometric perturbations. That's important for all of our stakeholders. And this forecast is going to occur multiple days ahead. So it's going to occur from 2 to 5 days ahead for a high-speed enhancement. So this high-speed enhancement, for instance, this is like 3 days ahead or so. So we're going to tell you what the geometric perturbation is like 3 days before it's actually going to happen. But if you really want a very high fidelity forecast, we also have the Dagger++. So where you actually consider the in situ measurements of plasma, and as the wind goes through, we have incorporated the measurement sparsity of these perturbation measurements. So remember that all of these models are trained on large data set. So the Dagger model is trained on 10 years of data. The sheath model is trained on 10 years of AI data, which from the SDO-ML dataset. And the same thing goes for Dagger++. So all of this also depends on how much measurement sparsity we have. So depending on the measurement sparsity, and we also have incorporated the magnetospheric context in the form of geometric indices. And that's going to give us an enhanced TRL of Dagger++. What we have in Dagger++ is also deep ensembles to generate uncertainties of forecasts. So we not just give the forecasts themselves, but also uncertainties, which is very cool because that gives us a factor of safety of sorts to the stakeholders for them to be used. And this whole pipeline is end to end. It's integrated with SDO-ML. So as and when we keep getting AIA and HMI data from SDO-ML, we just run it through the pipeline through Sheath and Dagger and get the geometric perturbation forecasts. And then closer to the day of the actual event, we then start sampling solar wind measurements at L1 and then switch on Dagger++, get the state of magnetosphere and get high fidelity forecasts for very localized enhancements. So that is what the team really worked on during this whole period. So there are two main open questions that we have put that have been bothering us, if you want to take it in that manner, and these two questions have a science motivation and an ML motivation. The first question is, we have these coronal mass ejections which are not really captured by SDO-ML. You need some coronographic data, and the science part is, how do you automatically identify these CMEs, and how would you incorporate the properties of CME in an automated fashion with the existing code in pipeline? So this is both a science question because you need to know the exact features. It's also an ML question because we don't know what, or rather we are still thinking on what sort of algorithm can you use to identify stuff. On the Earth side, we have these very localized enhancements which occur over a length scale of hundreds of kilometers, let's say. And a lot of these localized enhancements are not captured. And that's because we need to have an appropriate representation of what these enhancements are. And that depends on the state of the magnetosphere. So given the state of the magnetosphere, what is the representation in the form of a basis function? And from an ML perspective, we can always ask, is it possible to learn this basis given the data? So I will leave that here, and let's have a discussion on this work from our great panel. Thank you.
Thank you so much, Vishal. If you'll stop sharing, and I'll just ask our panel to weigh in on those open science and ML questions that you just posed.
I think what the team has already done is not dagger, but pretty staggering. I can tell you over the past 15 years, in the Living with the Star program, the goal has been to do sun to mud modeling, where scientists come together and connect this, but with physics-informed models. And what you're doing, and in those kind of situations, they are not being able to incorporate all the variety of data we have. And what this kind of approach is doing, we are utilizing the data. Data is our ground truth. In physics, we can add many different kinds of parameters and make something fit or not. But these are all, as I see them, you're taking something, observations taken 93 million miles away, and you're connecting that to, global geo-effectiveness. And we want this because we want the power grid operators to be armed with the information that something big is coming that's going to change their voltage, and they need to turn their transformers off. This is quite remarkable. And it's built on sort of successive FDLs from the past. I mean, it all just seems like we had already envisioned the grand success of this program and approached it that way, but it's all come together really coherently and beautifully. Thank you very much.
Thank you, Lika.
And I think that I would like to... Go ahead, Mas.
I'll add my thank you, but also I love actually kind of the fact that this project is also building on the previous ones. I think actually kind of that's a great kind of pattern to kind of get better and better at things. I think actually this is awesome work. I think that actually ability to predict quickly and kind of shorten that time, to Lika's point, of course, can actually make us actually kind of being able to respond to those events that, of course, we don't control too much promptly. It's also kind of, I think actually it has also kind of interesting data implication. The quicker actually you can make a prediction, the more you can actually incorporate recent data in order for that in that prediction and making that prediction even more valuable. So I think actually this actually is also going in that direction, making this even more interesting. Sorry, Andres.
No. I actually was going to say something similar to what you said. And I think one of the things that I want to highlight that I think is awesome about this project is, we want to increase the lead time, right? And at some point we have to chain our forecasting tools. The majority of the tools that we have in heliophysics are, okay, I'm going to predict the flare. And then someone is going to predict the CME. And then someone is going to predict the impact on the ionosphere. Here, we're increasing the lead time by chaining two, right? And this ties to one of the final questions that Vishal mentioned. It's like, okay, we have to do CMEs, and there are things that people have built to forecast CMEs, but they have not chained them all the way into the forecast of the ionosphere. And I think that integration and this connection of our forecasting capabilities is something that is really cool about this project.
Thanks. Hunju or Tom, do you want to weigh in?
Yeah, I just want to second what Andreas just said and congratulate the team on really doing two things this summer. The sheath model is an entirely separate model from Dagger, and that's quite an accomplishment to have done. Not only upgraded the Dagger model, but to have added this, as Andrea said, a chained solar wind prediction model that makes the lead time even that much better for the Dagger model. So really impressive work. I also want to emphasize that, yes, the CMEs are needed because those are the ones that cause the big geomagnetic storms, both for the geomagnetically induced currents and for the thermospheric effects that we'll see in the next talk. So it's great to see that you're going in this direction of providing more and more lead time through more chained forecasts of key phenomenon from the sun.
Thanks. Anshu.
If I could chime in, and you called my name, right? If I
Yes.
heard correctly. Oh, yes. Yeah, thank you very much for the FDL-X team. Yeah, just like the other panel members, I think a big improvement in the model compared to the previous one is to increasing the forecast time in advance. So we've been always depending on the L1 point data products, and then to predict what the geomagnetic activity is. So in that way, I think this modeling efforts are really going forward to increase the lead forecasting time. And I also know that this team working on the ionosphere magnetosphere data, which is also between the solar wind and the ground, right? So I would love to see their improvement in future as well. Thank you.
Wonderful. All right. Thank you very much, panel. We have our last presentation coming up, if I can just share my screen. And so the last presentation is from the thermospheric drag team, where we're looking at, can we better understand the importance of EUV on thermospheric drag? And this team was made up of our researchers, Shresh Malik and James Walsh, and our faculty, Giacomo Tom Berger, who's on our panel today, and Gunesh. And Giacomo has created a video for the presentation, because he is currently presenting at AMOS some of these results. So we'll go ahead and do the video share. Give me just a moment to get that up.
Hello, everyone.
And then if I can get confirmation that you can hear this.
Thank you for giving me the chance to speak today. So the goal of the thermospheric drag team this year was to...
Sorry, can somebody confirm if you can hear the video?
We can hear.
Okay, perfect. Let me restart it. And here's Giacomo. I do want to indicate that Giacomo this video has been edited for time, so he will not run over time. James, sorry, you won't get to use your thing. But there's a little bit of chop in there if you see it. It's just the editing for time. So, all right, here's Giacomo.
Thank you for giving me the chance to speak today. So the goal of the thermospheric drag team this year was to find ways to help ensure an effective space traffic management. And as you all know, the low Earth orbital domain population is rapidly growing. As these objects grow, it also grows the probability of collisions between objects. And mostly this probability of collision is associated with the fact that the estimation of states in low Earth orbit is uncertain, particularly due to uncertainties in thermospheric density estimations. So the consequences of this are real, because for instance, in February 2020, SpaceX lost 40 satellites due to a geomagnetic storm that was not properly predicted. So the thermospheric density estimation is a problem that must be tackled if one wants to reduce uncertainties in the determination of the position and velocity of the satellites. And this is a very complex and interconnected system, because it involves the interaction of the sun, the sun magnetic field, and the irradiance with the Earth atmosphere. So as it was discussed already by other teams, the sun, through both irradiance and its magnetic field, interacts with the Earth atmosphere, thereby causing variations in thermospheric densities, which in turn affect the motion of satellites in low Earth orbit. So the main research question of this year's FDL team was, can we better model thermospheric density changes by integrating high cadence EUV images directly, rather than relying on daily proxy indices? Through the Solar Dynamics Observatory, which is a NASA mission observing the sun since 2010 And thanks to also the SDML dataset that was prepared from an FDL project in 2019, we have high cadence calibrated and machine learning ready data with SDO images for both the AIA channels and the HMI channels. All these components present a unique opportunity to integrate them and leverages SDML images and to see their importance in thermospheric density variations. Our approach was to combine the Karman model and the SDML images to try to predict the thermospheric density estimations. So first of all, it was important to embed the SDML images because as we are talking about terabytes of data, so we produce a lower dimensional version of these images, which can then more easily be fed into machine learning models for downstream tasks. And for this, we used a variational autoencoder. And once the SDML images are well represented by the autoencoder, this means that from terabytes worth of data, one is able to extract features that are a few hundred megabytes. And from this feature, using the encoder part of the variational autoencoder, one is able to reconstruct the full images. This was important because it allowed us to, first of all, produce a very, very lower computationally heavy version of SDML data because these embeddings are only a few hundred megabytes worth of data. And secondly, because they can be much more easily used for downstream tasks. So the next step was to include this SDML data, actually their embeddings inside thermospheric density models. And this was the main goal of this year's team and what the researchers mostly worked on. So one of the first events in which we tried this and in which the researchers assessed the performance of the model was the geomagnetic storm on the late September 2017. This allowed us to have a shared event among the teams through which we could integrate all our pipelines. And the team indeed discovered that the model with SDML images could very well predict this geomagnetic storm event, although of course there are still some accuracy improvements that could be achieved. So in summary, reducing the uncertainty in drag enables larger Goldilocks zone for LEO satellites, and in general a better understanding of the Sun-Earth interaction via thermospheric density prediction and SDO images is very important. And this is the first step towards that goal, because by investigating the importance of SDO images inside thermospheric density models, one is able to tell which solar features and which solar events played a bigger role in thermospheric density estimation, and to quantify actually that with numbers. So we have seen that SDML is able to replace the solar proxies and enables a live high cadence thermospheric density inference pipeline. We can group the results into three main groups. First of all, the team achieved what we call encoding the sun. So it produced an SDL embeddings version of the SDML dataset. As I said, this is a few hundred megabytes worth of data through which you can reconstruct the full images. Then it also used these embeddings to assess their importance for downstream tasks such as F10.7 or other solar proxies prediction. And there they confirmed that these embeddings can be used for this task. And also that since these images come with a higher cadence, you can directly use the SDML embeddings to also reproduce a high cadence version of the proxies, which is therefore also more useful for thermospheric density estimation, even if you don't go directly into the SDML embeddings integration, but you just use a higher cadence version of the proxies. Finally, it was investigated how these SDML images play a role in thermospheric density models and how they can replace solar proxies and still maintain the same accuracy. So improving the thermospheric density model embedding SDM images is important because A, it ensures a safer space traffic management, B, it reduces the errors in thermospheric density modeling, and C, it allows to assess the impact of UV irradiance in thermospheric density modeling. And with this, I would like to thank you very much.
Wonderful. Thank you, Giacomo, who's not here. And I will once again open it up to the panel. Giacomo did a good job of talking about what some of the impacts of that are in terms of space safety, but I'm wondering from the panel, what other opportunities do you see that this research would unlock, or what other comments do you want to add to this presentation?
Okay, I'll start off by saying that like the last presentation, we did an enormous amount of work this summer to get the model to the point where it is now predicting thermospheric density changes due to solar irradiance changes, but we don't yet have CMEs in there. So there's a whole nother step that needs to be done to really capture the geomagnetic storming in thermospheric density changes. And I really look forward to future FDL projects that will incorporate this as well.
I think a component I would like to add is what is really astonishing is that we are where we are with the mission that launched one solar cycle ago. And one magnetic solar cycle ago, when we actually created the Living with the Star program, this was the dream. You know, when we launched SDO, this is what we expected. And that realization is coming true about now by utilizing the full potential of the SDO observations. And it's not just for planet Earth. I mean, we heard a lot about the drag, the space traffic management, as Tom mentioned. We will need the particle components, but this is huge. Absolutely so much better than anything else we have had. But this is something that we can now begin to transport to other planets. You know, going to Mars, going to Venus, aerobraking, whatever you can imagine that we would like to do at other planets. This EUV modeling capability that was demonstrated last year, that you can do it from a solar system perspective. These are really game changers from my vantage point on Earth. Thank you, guys. Fabulous job.
Yeah, +1 on the fabulous job. And I think, again, kind of the ability to predict the impact of these phenomena, it's massive. I mean, just think about satellites and kind of other aspects of our daily life. One kind of suggestion here is that in other contexts, we've found actually that when we build this embedding representation, they get actually kind of really, really semantically charged. And so to the scientists among us, it would be also very interesting to understand what are the physical correlates of those embeddings, if there are any. Can we actually kind of, move in this embedding space and kind of characterize real physical phenomenon? And actually that actually may help us actually understand better even how the physics behind all of this actually works. But yeah, amazing job. I mean, this is really massive.
Nice. Andres?
Yeah, I also wanted to highlight, I think, how this team is really modernizing how we're doing the forecast of these densities. For a long time, aspirationally, we have wanted to use ultraviolet and just the ultraviolet spectrum and to harness, the possibilities of the images themselves. And I think this team finally brings that aspiration to reality. Because it opens very interesting possibilities when we move into an operational setting, right? I think there is a historical reason why we were doing forecast of these densities using not using ultraviolet and so on. But we have now operational satellites that are measuring ultraviolet, and so the future is now, and this team is bringing that kind of forecast into the present and moving it into the future.
All right. Well, we are almost at time. I want to just open up one last question for the panelists. And James, if you want to weigh in as well. And that's, what have you learned from this experience? So we've heard it a bit so far, but I'll just ask each of you to give us a statement on that. And Hunju, I'll start with you.
To me, what I learned is we need more data to train our models better. And when we discuss about the thermosphere, drag analysis, and we discuss what if we can contact to the commercial satellite companies and then get their satellite, drag data so that we can utilize that data for, thermosphere density forecasting. So I think more collaboration needed between the science community and the commercial community. And I hope that Lika could continue to push this end. Thank you.
Thanks. Allison.
Yeah. Final thoughts, of course, to just the whole program. It's just victory again. I don't have a camera, but it's like fist pumping that we've achieved everything that we have. But A reminder as well that, especially in this instance, AI-based forecasting is evolving extremely rapidly. We now have Fourier neural operators with spherical harmonics. So, we've already gone from the physics informed side to now realizing that you have to address geometries, that we're dealing with spheres here. And so taking away the typical mesh and grid based physics that we're dealing with. And that in itself, the F&O part is really important because it's so fast and so quick to compute, providing you have that compute. And, again, a reminder, NASA and NCCS at Goddard, they all have, 4 ampere nodes there. They have a lot of our compute, and even that's getting quicker and quicker. But the speed and if you're using this really up to date AI-based forecasting techniques, is increased certainty. And that just comes with the fact that you can run thousands of models at a time, not just 5 or 10, but thousands of models. So you get massive certainty. So really excited to see all that going, and FDL again moving along with the field. Fantastic work, everyone.
Thank you. Lika.
My final thoughts. I wish, our research budget was keeping pace with the technological advancement. And I want to I have an aspiration, and I'm going to state it based on what Alison said in the very beginning. She correctly mentioned that the number of areas that this is going to affect, we haven't thought through all of this. And if NASA could only monetize its own data, then we would have the research dollars to support amazing activity. Just a thought.
Wonderful. Yes. Tom, do you want to weigh in?
Just a final thought that I need to learn how to get less sleep so that I can work more with these guys across the pond. It was a fantastic experience. I really would like to do more intensive work of this type. I think FDL-X has shown you can accomplish an amazing amount in a very short amount of time if you have the right team, the motivated problem, and the tools to address that problem. It's been a fantastic experience.
Wonderful. And Massey?
Sorry, I was looking for my button. I think actually again, this actually is true for FDL. I'm always amazed by what you can accomplish in a very, very short time. I think that to me is the big take-home message, because a lot of these projects can be done in many settings and with many different resources. But doing them so fast and kind of making a dent this quickly, I think it really takes FDL. And so I think actually that's is my call out here about actually the awesomeness of this program.
Nice. And Andres, do you want to close us out with final thoughts?
Yeah, I wanted to highlight the fact that the FDL as a program was missing something that in the medical community they call from the lab bench to the bedside, right? And it is the idea that you can do a lot of research and a lot of development and prototypes and everything that teaches us a lot, but how do you make it so that now you can take it into the patient's lives? And I think the FDL-X it's a really successful experiment when it comes to taking things that we have accomplished, successes of prior FDLs, and really take it the extra mile so that it now is making a true impact, a true societal impact. And that's what I wanted to highlight, that success.
Wonderful. With that, I would like to once again really thank our sponsors and our panelists. Again, all of this successes is not possible without NASA and Google and NVIDIA. So everything that you have brought has been amazing. And I'll let James have the final word before we exit this live stream. James, you're muted.
Oh, thank you, and I'm sorry my sound effect plan didn't come together, but I think everyone was so efficient, we didn't need it in the end. Yeah, I'm sort of blown away too, because I think there's, I really love the analogy of the mouse and the milk, and the mouse keeps on churning, eventually turns the milk into butter and climbs out of and there's something about that with the process that went through this year. Like it was hard work, and I really wanted to, congratulate and acknowledge the efforts of the researchers and the faculty to really pull off, 3 really extraordinary outcomes. Really hats off to you all, and thank you so much. But of course, it's a team effort. It's, we've created a really nice community, and that is part of the success formula. And it's really quite hard to sort of describe this to people when you say, how does FDL work? Why does it matter? It's because, of course, we've all become friends. And so I just wanted to say thanks to everybody for believing in the dream and helping this work, and really looking forward to what comes next.
Wonderful. Thank you, everyone, for joining us on this live stream today. And to our panelists, have a wonderful rest of your day.
Take care. Bye-bye.
Thanks, everyone. Bye.
Thanks, Anne.
Bye.
Bye.
Thanks, everyone. Bye.